a unit called the radian. A radian is defined as the angle subtended at the center of a circle by an arc whose length is exactly equal to the radius of the circle. Let's look at this circle. If the radius is r, and the length of the arc from A to B is also r, then the angle theta at the center is exactly 1 radian. Because the arc length is directly proportional to the angle at the center, we define the angle in radians as the ratio of the arc length to the radius. This is why radians are often considered a dimensionless unit. It is simply a ratio of two lengths. This mathematical elegance is why radians are the standard unit of measurement in calculus and advanced trigonometry. To work effectively in Cambridge 9709, you must be able to switch between radians and degrees instantly. Let's derive the relationship using a full circle. The circumference of a circle is given by c equals 2 pi r. Since a full revolution corresponds to an arc length equal to the circumference, we can find the total angle in radians. When we divide the circumference by the radius, the r terms cancel out, leaving us with 2 pi radians for a full circle. This gives us our fundamental identity. 2 pi radians equals 360 degrees. Dividing by 2, we find that pi radians equals 180 degrees. From this, we derive our conversion factors. To convert degrees to radians, multiply by pi over 180. Conversely, to convert radians to degrees, multiply by 180 over pi. Memorizing this identity is far more efficient than memorizing two separate formulas. Always check if your answer should be in terms of pi or as a decimal. Let's focus on a key concept, the common angle equivalence. In A-level mathematics, fluency with exact values is a hallmark of an A-star student. You should be able to recognize these standard angles immediately without reaching for your calculator. Let's look at the standard conversions. 30 degrees is pi over 6, 45 degrees is pi over 4, 60 degrees is pi over 3, 90 degrees is pi over 2, 180 degrees is pi, 270 degrees is 3 pi over 2, and finally, 360 degrees is 2 pi. A helpful tip is to use 180 degrees as your anchor. Since 180 is pi, 90 must be half of that, or pi over 2. Similarly, 60 is a third of 180, so it becomes pi over 3. Understanding these as fractions of pi will prevent simple calculation errors during time-pressured exams. Example. Let's apply our conversion factor. We want to convert 135 degrees into radians, leaving the answer in terms of pi. To go from degrees to radians, we multiply by pi over 180. This gives us 135 over 180 times pi. Now, we must simplify this fraction. Both numbers are divisible by 45. 135 divided by 45 is 3, and 180 divided by 45 is 4. So, the result is 3 pi over 4 radians. Leaving your answer as an exact fraction of pi is often required in pure mathematics 1, unless the question specifically asks for significant figures. Now, let's convert 5 pi over 6 radians into degrees. Here, we use the inverse conversion factor. Multiply by 180 over pi. Notice how the pi in the numerator and denominator cancel each other out perfectly. This leaves us with 5 times 180 divided by 6. We can simplify 180 divided by 6 to get 30, which equals 150 degrees. This method is reliable and prevents you from accidentally flipping the conversion fraction. The true power of using radians lies in how much it simplifies our geometric formulas. When the angle theta is measured in radians, the relationship between radius and arc length becomes incredibly straightforward. Because a radian is defined by the ratio of arc length to radius, the arc length s is simply the radius r multiplied by the angle theta. No more complicated fractions of 360 degrees. Similarly, the area of a sector is simplified. Think of this as being analogous to the area of a triangle, which is half times base times height. In a sector, the base is the arc length r times theta, and the height is the radius r. Note a vital exam warning. These two formulas only work if theta is in radians. If you are given an angle in degrees, you must convert it to radians first, or your result will be incorrect. Let's look at a typical Cambridge 9709 style question. The diagram shows a sector of a circle with center O and radius r. The angle at the center is alpha radians. The perimeter of the sector is 20 centimeters. A. Express r in terms of alpha. Given that the area of the sector is 25 square centimeters, find the value of alpha. For part A, we need the perimeter. The perimeter of a sector consists of 2 radii and the arc length. Since arc length is r times alpha, the perimeter is 2r plus r alpha. We are told the perimeter is 20. Factoring out r gives 20 equals r multiplied by 2 plus alpha. To express r in terms of alpha, we divide by the bracket. For part B, we use the area formula. Now, we substitute our expression for r from part A into this equation. Simplify the squared term. 20 squared is 400. Half of 400 is 200. So we have 200 alpha over 2 plus alpha squared equals 25. Divide both sides by 25 to make the number smaller. 200 divided by 25 is 8. Expand the quadratic on the right and rearrange everything to one side. This is a perfect square. Alpha minus 2 squared equals 0. Therefore, alpha equals 2 radians. This step-by-step substitution is a common requirement in pure Math 1 exams. In Cambridge examinations, students frequently lose marks on circular measure due to avoidable errors. Perhaps the most common mistake is leaving your calculator in degrees mode when solving problems involving the arc length or sector area formulas. Since these formulas are derived specifically for radians, using degrees will give a completely wrong numerical value. Always check for the R symbol on your screen. Students often forget that the perimeter of a sector includes the 2 radii. If a question asks for the perimeter, you must calculate the arc length plus 2 times the radius. Using only the arc length is a guaranteed loss of marks. In Pure Mathematics 1, you should keep your answers in terms of pi for as long as possible. Rounding pi to 3.14 early in a calculation leads to rounding errors in your final answer. The Cambridge mark scheme is very strict. If your answer is not accurate to 3 significant figures, you will lose the final accuracy mark. Students often confuse the area of a sector with the area of a segment. To find the segment area, you must take the sector area and subtract the area of the triangle formed by the 2 radii and the chord. To maximize your score in the 9709 paper, keep these professional tips in mind. Examiners often mix degrees and radians within the same paper. Always check the interval given for theta. If you see 0 to 2 pi, use radians. If you see 0 to 360, use degrees. In multi-part questions, examiners award method marks for correctly substituting values into the arc length or area formulas. Even if your final answer is wrong due to a calculation slip, showing the formula with your numbers plugged in secures those crucial marks. Use the pi button on your calculator rather than 3.142. For questions where you must provide a decimal answer, the standard Cambridge requirement is 3 significant figures. However, for intermediate steps, keep at least 4 or 5 figures to maintain precision. If a diagram isn't provided, draw one. Label the radius, the angle, and the arc. Visualizing the relationship between the components often reveals the path to the solution, especially in questions involving perimeters or shaded regions. It is time to test your understanding. Please pause the video and attempt these 3 questions before checking the solutions. The first question is a simple conversion. Convert 210 degrees to radians, giving your answer in terms of pi. For the medium challenge, a sector of a circle has a radius of 8 centimeters and an arc length of 12 centimeters. Find the area of the sector. Finally, the hard question. The perimeter of a sector is fixed at P. Show that the area of the sector is maximized when the angle theta is 2 radians. Take a moment to solve these now. Let's look at the homework solutions. For the easy solution, to convert 210 degrees to radians, we multiply by pi over 180. Dividing both by 30, we get 7 pi over 6 radians. Now for the medium solution. First, we find the angle theta using the arc length formula. Plugging in our values, 12 equals 8 times theta, which gives us theta equals 1.5 radians. Now, substitute this into the area formula. Area equals 1/2 times 8 squared times 1.5. Calculating that gives 0.5 times 64 times 1.5, which is 48 square centimeters. Finally, the hard solution. Let perimeter P equal 2r plus r times theta. Rearrange for theta. Substitute this into the area formula. Simplifying, area equals 1/2 PR minus r squared. To maximize area, we differentiate with respect to r and set the derivative to 0. This tells us that P must equal 4r. Substitute P back into our perimeter equation. 4r equals 2r plus r times theta. Subtracting 2r from both sides, we get 2r equals r theta. So, the angle theta is 2 radians. To wrap up, here are the key takeaways. First, pi radians is equal to 180 degrees. Second, the arc length formula is S equals r theta. And third, the area of a sector is 1/2 r squared theta. Always ensure your angle is in radians before using these formulas. To conclude, ensure you have mastered these core concepts for your examination. First, remember that a radian is a ratio of arc length to radius. This dimensionless property makes it the essential unit for all higher-level mathematics. Second, the relationship pi equals 180 degrees is your primary tool. Use it to derive the conversion factors, pi over 180 for radians, and 180 over pi for degrees. Third, the formulas for arc length and sector area are remarkably simple in radians. Always double-check that your angle is not in degrees before applying them. Finally, maintain high precision. Work with exact fractions of pi whenever possible, and only round to 3 significant figures at the very final step of your calculation to satisfy Cambridge marking criteria.